Hello, this is Mr. Huff. Let's look at simple beam analysis. This is part 2, and we're looking for reaction forces in this slide deck. So this is the first step. You're going to draw your simple beam, label this side A and this side B to follow along with this. Just a point to make here, actually work this out in your notebook along with me. Just reading this, it won't make sense. If you write it down, it's easier to understand, okay? This triangle here is a pinned connection. This means the beam can rotate up and down, but it can't move left and right. And then over here we have a roller. This means the beam can move left and right, but it cannot move up and down. And then we're going to do this to scale using grid paper. Usually if this beam is like 20 feet long, use 20 boxes. So 1 foot per box is usually what you can do. And that will help you get to the right answer. All right. Another thing is we also need to consider the uniform load. So this beam, it has mass. And it's usually given to you in pounds per foot. So you just take the pounds per foot times the length of the beam, and that will tell you the weight of the beam, and the weight is distributed with these little arrows uniformly from one side to the other. So that's the other part we're taking into account. In Principles of Engineering or Engineering Science, you didn't do this part. You just looked at the forces acting on the beam. You didn't consider the weight of the beam itself. In this case, we're also including the weight of the beam. So your simple beam diagram might look like this. So you have your pin, you have your roller, you have your point force or your concentrated force, and then your overall uniform loading for the beam. We also have it labeled A on this end and B on this end. So that's what your drawing should look like. Normally, the free body diagram is drawn right below and aligned with your drawing, so give yourself a little bit of space to work above it and below it. The free body diagram helps us understand the forces acting on the beam. So that's the reason we're doing this. So you just line them up. So if you're, okay, here we go. So we're going to do some things here. We're going to call the point force LP, and we're going to call the uniform load LU. Just working our way from the left side to the right side. This is at point A. We're looking at the force in the X direction and the Y direction. This is how we define a pin on a simple beam. And then the next number we're interested in is it's 6 feet from the pin to our, that is not what I wanted to do. It's 6 feet from our pin to our point load, which is 4,000 pounds. That means we have 14 feet left because this beam overall is 20 feet long. We also know that our uniform load is 650 pounds per foot in this problem. And then we have over here the reaction force in the Y direction at point B. So this is what your free body diagram will look like with its labels and everything. Okay, so this beam is in static equilibrium. Therefore, these have to be true. Our sum of forces in the X direction and the Y direction need to be equal to 0. And our sum of our moments need to be equal to 0. Forces in the X direction are easy. If you think about your drawing, there are no lateral forces acting on it. So that means our force in X at point A is 0 pounds. So really, for our problems we're going to be doing, you can just leave the force of X A out and just do your calculations from there. But we're going to add this to the free body diagram. So we put, this is 0 pounds. Now we're looking at the forces in the Y direction, and this gets a little more complicated. So we're going to say that if it's pointing up, it's positive, and if it's pointing down, it's negative. So our sum of forces has to include the reaction force at point A, the reaction force at point B, the point load, and the uniform load, and the sum of all this has to be 0. Notice that these two are pointing down, so they're negative. That means we're going to replace these numbers with what we know. We don't know the reaction forces, but we do know that the point load is 4,000 pounds and that the weight of the beam is 650 pounds per foot, and there's 20 feet, so we multiply those together and we get 13,000. And that means we can say that YA plus force YB minus 4,000 minus 13,000 is equal to 17,000. So here's that little bit of algebra, and we end up with a total reaction force in the Y direction of 17,000. Let's go label that over here. Our reaction forces, YA, or force at YA, force YB, is equal to 17,000 pounds. Now we have to look at moments. Moments are all about rotation. It's force times distance. So you have a force and the distance from the axis or the point, the center point of the rotation. We're going to say that counterclockwise is positive and clockwise is negative. And this goes along with the Cartesian plane. If we start over here and we go this direction, we're increasing from 0 degrees to 90 degrees to 180 degrees. That is a positive increase. If we go from 180 to 90 to 0, we're subtracting, so this direction is negative, this direction is positive. So let's look at our moments. We have a moment here that we have to account for at point A. We have a point load, we have a uniform load. Let's talk about this. This whole beam is 13,000 pounds. But we need to think about it in terms of center of gravity, which means it's right in the middle. So 20 feet long divided by 2 tells us that the center of gravity is at 10 feet, right here. So we're going to have 13,000 pounds acting right here. So that's the distance for force times distance is 10 feet for our uniform load. And then over here we have the reaction force at point B, 20 feet from point A. All right, so we need to let's start with moments. I'll try to make this easier to follow through. So I'm going to start by looking at the moments. So we're going to say the sum of the moments, the moment in Y at A, the moment at YB, the point load moment, and the uniform load moment has to be equal to 0. We're going to take those and turn it into force times distance. So the force right here times 0. That's going to be 0. We can get rid of that because it's going to be 0. The reaction force at point V times 20 feet. The point load times 6 feet. The uniform load times 10 feet is going to equal 0. Notice that these are going counterclockwise. They push up in our diagram. These push down, so these two are negative. This one goes up. These go down. All right? So that's why we have positives here and negatives here and here. All right, so we're going to get rid of that reaction force at A. That means reaction force at B times 20 minus 24,000 minus 130,000 from this equals 0. So we can rearrange this section now to show that our reaction force at B is 24,000 plus 13,000 divided by 20. And if you calculate that, that means reaction force B is 7,700 pounds. Write that down on your diagram. So we're going to add that number over here. So now we know this, and we know that these two together equal 17,000. We can find this. Recall that we determined the total reaction forces in the Y direction is 17,000 pounds. We just determined that the reaction force, FYB, is 7,700 pounds. Now we can find FYA. So to find that, we're going to say FYA plus FYB equals 17,000 pounds. We're replacing FYB with 7,700 pounds and then solving for FYA. So FYA is 17,000 pounds minus 7,700 pounds, so we get 9,300 pounds. Go update your diagram right here. So we have found the reaction force at point A and the reaction force at point B. We can check our work. So if we remember, the sum of our forces needs to equal 0, so we have a positive 9,300, a positive 7,700, a negative 4,000, a negative 13,000, and that means that it's 17,000 minus 17,000, and that does indeed equal 0. Our math is correct. Just to recap, for finding the reaction forces in a simple beam, so we're going to draw the beam to scale. We're going to add a free body diagram labeling forces and loads. We're going to add values as we go. We are going to look at the sum of forces in X. As long as we don't have a lateral force acting, this is always going to be 0. The sum of the forces in Y, we're going to find the total reaction force. And then the sum of the moments to find the reaction force at point B. And then the total reaction force, we can find the reaction force at point A. And then we can check our work to make sure all of our acting forces indeed equals 0. And that is how you solve a simple beam to find reaction forces. All right, that's all for now. Thank you.